Hello guys, welcome to this new video. In this video we are going to solve a new problem. It's about dynamics. It's about a rotating rope which we attached it to two fixed points, and it is actually rotating with a constant angular velocity. And in fact we can actually find the shape of the rope, but in this question we are not going to find that. In this question we are going to find something else, for example the tension in the rope, or actually a kind of shape of this rope. You will understand it later, but in another actually question we are I will actually record it later, that we actually have a rope between two walls, and we want to find the shape of the rope. In For example, this is our system, this is our coordinate system, and we want to actually find the shape of the rope. But in this video we are not going to do that. We are going to do something else with this rope. It's somehow similar, but it is actually different. Okay, let's read the problem. As you can see in the picture, we have a rope with length L and uniform mass actually M, which is attached between two fixed points A and B, and it's rotating with constant angular velocity omega around the straight line AB. It's the straight line AB. The distance between each point of rope, for example this point of rope, for example, each point of rope, and the line AB is R. This is R, this is the distance, it is the distance. Pay attention that R varies for each point of the rope. Actually it is obvious. This tangent line of the rope makes angle theta with the horizontal at each point of the rope, and theta is not constant, it is theta. I showed it in the picture. This is theta, and actually the tangent line actually makes the angle theta with the horizontal at each point of the rope. For example, it is at this point of the rope. We have a tangent line, which it is red line, and it makes the angle theta with respect actually to the horizontal. With respect to the x-axis, we can consider that this is x-axis, x. And theta is not constant, it varies for each point of the rope again. This theta is theta 0 at point A, this is, and also minus theta 0 at point B. Suppose the distance between the rope's center of mass and the line AB is RCM. Okay. Part A of the question wants us actually to find the tension at the points A and B in terms of M omega, RCM, and theta 0. It means that we should find T0. Let me to copy this actually. Oh, sorry. Let me to copy this picture and paste it here to actually draw something else on it. Let me to clear this row and G. Actually, because of the symmetry of the question, our RCM is actually in the middle of the rope, because actually the question has symmetry. And we also have two T0s here, T0 and T0 here. And actually they make actually angle theta 0 with horizontal, and we know that we know of the definition, from the definition of the center of mass, that we can actually suppose that all external forces actually are actually entered to the center of mass. And also we should know that E is here. So actually here we don't have actually G. We don't have any gravity in this problem. Sorry about this. We don't have any gravity, because I was thinking about that. If we want to find the tension, it may be actually be a function of also the gravity, but here it doesn't say that in the terms of m omega rcm theta 0 and g. So it was my fault. We don't have any gravity in this actually in this problem. So we can consider, I was talking about that from the definition of the center of mass, we can suppose that all the external forces actually um, are that in the fact that they are entering into the uh, center of mass. So we can consider that this is the center of mass, and here we have two external forces T0 that they make angle theta's sorry about this. Sorry about this. We have T0s which they make angle theta 0 with respect to the horizontal, and also the actually distance between the center of mass and the line which it is rotating around it. This line, need to change the color, sorry, it is actually RCM. The question says that it is RCM and it is rotating around it. With constant angular velocity omega, and we know that if if we have for example, if we have a particle which it is actually rotating around the circle with radius r, it is a particle with mass m, and it is a circle with radius r, and it is actually rotating around it with constant angular velocity omega 0, for example. And then we have a central acceleration. We have a central acceleration which it is actually r, let me call it a, it is acentral, I call it acentral, which it is actually the velocity of the particle square divided over actually r, which actually v is r times omega 0. So if I substitute it in that, acentral is equal to r times omega 0 square. I suppose that you know about it. I just write it as a note. I don't want to prove it, but maybe if you want me to actually talk about it and prove it in detail, please comment down, and then I will actually record another video, and I will talk about actually the acceleration in all coordinates, for example in spherical coordinate or in Cartesian coordinate, or something like that. And I will actually show you that in the polar coordinate our acceleration will be something like this. In the actually polar coordinate system, our acceleration of a particle is going to be like something like this, which dot is actually the symbol of d. For example, let me write it here. R dot means actually dr over dt. But I don't want to talk about it. You just should know, for this problem you should just know that every particle that is going around the circle with actually constant velocity, constant angular velocity, has an actually central acceleration which it is equal to r omega 0 to power 2. So here, if I want to actually write the equations for the center of mass, if I want to write the equation for the center of mass, Newton's equation for center of mass, we have actually in this direction we have an acceleration, central acceleration, which it is actually r omega to rcm omega to power 2. So we know that sigma f is going to be ma. So we just have the central acceleration, so we have actually 2t0 sine theta 0 is equal to m, the mass of the rope, actually the mass of the center of mass, which it is equal to the mass of the whole rope, and a, which it is actually r cm omega to power 2. So from this we can obtain that t0 is equal to m times rcm times omega square over 2 sine theta 0. And this is part A of the problem. This is part A. So let's go to the part B. It says that write Newton's second law for an small element of rope and find the tension at each point in terms of t0, theta 0, and theta. Actually, it's a trick. It's a nice trick, and you should be similar to how actually take small elements and actually write Newton's second law for them. And it will be a good exercise, this problem, it will be good exercise for actually this purpose, for this trick, to learn this trick. Let me to actually solve this. You can actually, for example, consider this small part of the, let me to change the color, for example, green. For example, take this part of this small part of the rope. If we actually zoom this part of the rope, we will see something like this. Actually, we will see something like this. Sorry about bad picture. This is a small element of rope. Okay, now consider that we have an x-axis, and here consider that here is x, and also here is x plus the differential of x, which it is dx. Here is dx, here is at the place x plus dx, and here is at the point x. So here was x, and also here is, let me to actually change it and draw this. For example, here is the origin, here is the origin, and it is x, and also dx is very small. You should know that dx is very small. It means that dx over x is very small. So you can consider that the tangent line here, we have a tangent line here. We have a tangent line here. Sorry, we have a tangent line here, and also a tangent line here at the point x plus dx. sorry about the bad line, which actually it has a mm, angle, which it makes angle theta with actually function of x. Here theta at the point x, and here it is theta at point x plus dx. And also we have a tension t here, have a tension called, we call it t of x here, t of x, with actually, which actually it is in the direction of the tangent line. And also we have a actually tension, which I call it tx plus dx. It means the tension at point x plus dx. And also this part of the rope is actually rotating around the line AB with the constant velocity, with the constant angular velocity omega. And we can suppose that this r, I want to change actually the notation. I wanted to call this r actually f of x. It means that for example, if here is x, if here is x, it is a function, it is a function of x, and it is f of x. So I want to change actually the notation, and I want to call it, for example, if you let me to erase it, for example, consider that this orange line is the line AB, which our element is rotating around, this A and this B, for example, and it is rotating around omega. And also this is actually r, the function which I want to change the notation f of x. I want to call it f of x. They are the same. Okay. So actually, if I want to write the Newton's equation for this element, I want actually to write the Newton's equation for this element. So we have actually two directions, one in this direction x, and another direction which I want to call it y. So if I write the Newton's law, Newton's second law, we have two directions, one x hat, which we don't have any, actually if you paid attention, we don't have any acceleration in the x direction. So the net forces actually in x direction is equal to 0, and the net forces in the x direction is just tx plus dx cosine of theta at point x plus dx minus tx cosine of theta of x is equal to 0, because we don't have any acceleration in that. Actually, because this is theta x, and this is tx cosine of theta x, and we don't have any acceleration in the x direction. And if we want to write the y hat actually equations, I should write that we know that we have a central acceleration downward, central acceleration, a central acceleration downward, which it is equal to let me to change the color and write the that we have the central, a central, which it is downward, is equal to r omega 2, which it is actually f of x omega 2. But why did I take this r? Because we have two r's. One of them is this. Actually, we have two r's. You may ask question that why did you wrote actually here it is actually fx plus dx, means rx plus dx. why did I write r of x? Why actually didn't I write rx plus dx? Because actually rx plus dx is actually similar because dx is very small, and we can consider here in this equation, we can consider that rx of plus dx is similar to rx because of the fact that dx to over x is very small, and actually it doesn't change. Actually, if we take rx plus dx in this equation, it doesn't change our answer very much. But here for t and theta, actually t and theta, actually we should actually write tx plus dx and theta x plus dx, because it is our actually it has an actually um, big effect on our equations, but this rx plus dx here doesn't affects our actually equations very much. So I can actually replace rx plus dx with rx, and actually it doesn't change very much. So let me to erase these. Okay, so if we want to write the y hat direction, y hat actually Newton's law in the y direction, I should write that we have a e of x, t at point x, sine theta of x minus dx plus dx sine theta at point x plus dx. It is equal to the dm. It is the differential actually of the mass of the it is the mass of this differential element, and dm f r of x r at point x, which it is f of x omega squared. Okay, now we should actually find what is a dm. What is dm? Finding this. Actually, because the question says that our actually rope has a uniform mass m, we can actually say that if we find actually the differential, the length of this differential element, and if we multiply this by m divided over l, we can say that it is dm. Actually m over l actually is the actually it is the density, which it is the length density of the rope. So if I we can say I can call it actually lambda, and if I from these, if I actually multiply lambda with the differential, with the length of this differential element, I can say that it is the mass of this differential element. But now what is the differential, actually the length of this differential element? We know that here it is theta of x, and also this is f of x, and this is x. And how can we actually do geometric to find this length? In fact, we can actually do some assumptions. Suppose that this is the, suppose that, let me to change the color. Suppose that this is, we can actually here neglect the actually the curve here, and we can consider that the dl, the length, this part of our actually this part of our rope is actually a straight line. I suppose that you know how to do calculus, and how to I suppose that you know this fact, but I just want to write it to actually make a review. So here consider that this is dl, and here also we have theta, which theta is actually, if we suppose that this is a function, this is a function, and suppose that we have a function here. Suppose that here we have y and x, and this is a function f of x. And if you want to actually find a differential element on, if you want to find the length of a differential element of this actually function on this actually curve, you will do something like that. Suppose that here our function makes angle theta with the horizontal. Let me to do this. Suppose that here our function makes angle theta with the horizontal, which theta is, which tangent of this, it is the actually definition of derivation. So the tangent of this theta is equal to f prime of x, which it is df over dx. It is the definition of the derivation. So here tangent of this theta, so according to this, the tangent of this theta is equal to f prime of x, and also it is dx. This length is dx, is the differential of our movement in the x-axis. And also we should find actually with this theta and this x, we should find this L. So dx over dl is actually, it is some geometric, some trigonometric actually. It is some trigonometric actual calculations. Dx over dl is actually the definition of cosine of theta, and cosine of theta we can find it here by doing some trigonometric calculations, that 1 plus tangent square is equal to 1 over cosine square, which it is 1 plus f prime square. So actually from this equation we can understand that cosine of theta is equal to 1 over radical 1 plus f prime power 2. So from this equation and this equation, I call it 1 and call it 2. So with 1 and 2 we can obtain that dx over dl is just 1 divided by radical 1 plus f prime square. So dl is going to be, sorry, dl, the differential of the length of this differential element is going to be radical 1 plus f prime square dx. We found this in terms of x and also f of x. So by this note I will call it star equation. So by the star equation we understood that dm, we understood before that dm is lambda times dl, and by actually star equation we understood that dm is just lambda radical 1 plus f prime square and dx. So now I want to actually substitute it in the y hat equation. Y hat equation, we had tx sine theta of x, sorry about this, we had tx sine theta of x minus tx plus dx sine theta of x plus dx was equal to dm rx omega 2, which dm is lambda radical 1 plus f prime over 2 dx. And rx, we said that rx is actually f of x. We said that they are the same here. Or we actually defined f, which it is equal to r, for the actually simplification that we can actually see that we are working with a function. We are working with a one variable function. It is not something so hard. We are working just with a one variable function here. So I actually replaced r with f, and here I will do this: rx dm rx omega 2 omega square. Okay, you can see that in the left part, if I call t sine theta, as I can say, for example, I can define it as a, for example, a new parameter a of x. You can see that in the left part, you can see in the left part that we wrote actually something like actually in the left part we wrote something like a of x minus a of x plus dx is equal to lambda omega 2 f of x radical 1 plus f prime of x to the power 2 dx. And as you can see here, this is the differential minus differential of a. It is minus differential of a of x. It is the definition of the differential of a of x. And if we actually divide both sides by actually dx, we will understand that it is minus a x plus dx minus ax over dx. It is equal to lambda omega. It is equal to lambda omega square f of x radical 1 plus f prime square of x. And as you can see here, it is the definition actually if we actually have a limit while dx is going to 0, dx is going to 0. This is actually the definition of, this is definition of derivation. So here we have minus dA over dx is going to be lambda omega 2 fx radical 1 plus f prime 2. And also we said that a is just t sine theta, so I can write here that d t sine theta over dx is going to be minus lambda omega 2 f of x radical 1 plus f prime x square. So we obtained this equation. It is y hat equation, and also x hat equation was just this. It was x hat equation. It is just x hat equation, which actually again it is the actually the definition if we divide both sides by dx. Again, this is the definition of derivation. Again, it is the definition of derivation. It is d. If we divide both sides by dx, it is going to be, sorry about actually the interruption. I don't know what happened to my OneNote actually. Okay, we understood that if we actually subtract both sides of this equation with by dx, we understand that it is actually, again, the left side is the definition of derivation. So the derivative of t cosine theta is going to be 0, and if the derivative of some derivation of something is going to be 0, so that element is actually constant. So t cosine theta is going to be some constant, for example, we call it c. So in the x hat direction, we understood that t cosine theta is some constant, and in the y direction we understood that d over dx of t sine theta is going to be minus lambda omega to power 2 fx radical 1 plus f prime 2x, sorry about this, radical. So actually we just actually wrote the equations. The part B says write Newton's second law for a small element, and it wants us just to find the tension at each point in terms of t0, theta 0, and theta. But how should we do that? We can actually use the x hat equation and find actually this c, this constant c. But how can we find that? At actually theta equals 0, we have just t we had tension t0, and cosine theta 0 is equal to t cosine theta. So t of theta, t is going to be something like t0 cosine theta 0 divided by cosine theta. It is part actually, this is actually, what happened to this? Cosine theta, this is actually part B. Okay, the next part, once it's actually, it is part C. It says that from the above equations, it means that from these two equations, which I wrote in two directions, x hat and y hat, it wants us actually to obtain an equation in this form. F, or it was actually f of x, and don't be confused with these two f's. And this f that we define here, this f that we define here is not equal to this f. Actually, this f is something else. It wants us to actually obtain an equation in the form r square is equal to f of theta, and find f of theta. So maybe it is obvious that we should actually use the second equation here. So how can we use this second equation? We can actually substitute. Here we have t, we have sine of theta, because sine of theta actually is related to tangent of theta, which it is actually f prime of x. But here we don't have t. What should we do with this t, actually we can actually replace and substitute this t with the answer of the part B. So if I actually substitute the t of the part B in the y hat equations, I obtain that d over dx of t is d0 cosine theta 0, and tangent of theta, which it is f prime of x, is equal to minus lambda omega to power 2 f of x radical 1 plus f prime of x square. And also we know that t0 is something like this. Let me to copy this and paste it here. So here we have actually, from these two equations, we have m omega to power 2 rcm divided by 2 cosine of theta 0 over sine of theta 0 is equal to minus, and lambda is also m divided by l, omega 2 f of x radical 1 plus f prime of x square. So here we can actually eliminate these m and omega 2 from both sides, and we can do this and just write something like this, that L R cm cotangent of theta 0 divided by 2, so here we have d over dx f prime of x is f double prime of x, because d over dx f prime of x is just f double prime of x. So LRCM over 2 cotangent of theta 0 times f double prime of x is just minus f of x radical 1 plus f prime 2 of x. And we can say that this parameter is just a constant, which I want to call it alpha. So we obtained from here that alpha f double prime is just minus f radical 1 plus f prime square. So here we obtained the differential equation for actual f, which it is actual r. We said that f of x is equal to r of x. But how should we actually calculate this differential equation? How can we solve this differential equation? There's another note which I want to tell you. There's a note here which we use actually a chain rule in this, and this is that you can write f double prime something like, it is something like df prime over dx, and we can use the chain rule here, chain rule in calculus, and we can write it df prime over df multiply with df over dx, and it is just df prime over df, and it times df over dx is just f prime. So we obtain that f double prime is df prime over df times f prime. We obtain this here. From this note, we can actually substitute f prime here with this, and we can obtain that alpha f prime, which is alpha df prime over df times f prime is just minus f radical 1 plus f prime 2. And here we obtained actually we obtained a differential equation with we can actually solve it. We can actually do this something like that: alpha integral symbol that we can write here, f prime over radical 1 plus f prime 2 df prime is just minus f df. Here we obtained this equation, and we can actually solve this equation. I consider that you know how to solve these integrals. Actually, if you take 1 plus f prime 2 as u, you will obtain that it is alpha actually du over 2 radical u, and here you obtained a minus f2 over 2. And if you solve this integral here, you will obtain alpha radical u is equal to minus f squared plus c, which is a constant, and u was nothing, just alpha radical 1 plus f prime 2 of x. It is equal to minus f2 of x divided by 2 plus c. But we know that f prime of x was just tangent of theta, and f of x was nothing, just rx. And if we replace our equation with these two assumptions, we will actually understand that it is alpha radical 1 plus tangent square of theta is equal to minus r square over 2 plus c. And we understand here that it is alpha over the absolute value of cosine theta is equal to minus r squared divided by 2 plus c. And because our theta here changes just from theta 0, our theta is just between theta minus theta 0 to theta, and theta 0 and theta are actually it is greater than minus pi over 2, and it is also less than pi over 2. So the cosine of theta is always positive. So here we can obtain here that alpha over cosine of theta is equal to minus r squared divided by 2 plus a constant. But what is this constant actually? How can we obtain this constant? Actually, we should actually use the initial conditions. What are the initial conditions? While theta is equal to theta 0, r is equal to 0. R is 0 here. As you can see here, when our theta is equal to theta 0, our r is 0. Actually distance between this point of the rope from actually the line AB is 0. So if I put this actual initial condition in this, I can obtain that alpha divided by cosine theta 0 is equal to c. So I can obtain from these equations that alpha over cosine of theta is equal to minus r squared over 2 plus alpha divided by cosine theta 0 okay, and so r squared divided by 2 is just actually alpha 1 over cosine theta 0 minus 1 over cosine theta, and I can say that r 2 r squared is just 2 alpha, which alpha was just this. It was alpha. Let me to copy this and paste it here. And if I multiply it by 2, I can eliminate this term. 1 over cosine of theta 0 minus 1 over cosine of theta, which actually we found something like this. So f of theta is just L RCM cotangent of theta 0, 1 over cosine of theta 0 minus 1 over cosine of theta. This is actually part C, I think. This was part, yes, it was part C. This is part C of the problem. Let's go to the next part. It says that now find the tension of the rope at each point in terms of R and other constants. Okay, now what was the tension at each part? We understood that the tension at each part is T equals to T0 cosine theta 0 over cosine of theta. It means that we should find cosine of theta. If we find actually cosine of theta in terms of R here, we can obtain what is T. Let me to copy this and paste it here. We found that T is something like this, and also we understood here that from part C, we understood that R2 divided by LRCM tangent theta 0 plus 1 over cosine of theta 0 is just 1 over cosine of theta. Let me to check it if it is true or not. Yes, it is true. So if I actually, let me to actually make the common denominator minus R2 sine of theta 0 divided by L RCM cosine theta 0 plus 1 over cosine theta 0. Let me to multiply it with R by all LRCM, and here you will have LRCM. It is equal to 1 over cosine of theta. So LRCM minus R squared sine of theta 0 over LRCM cosine of theta 0 is going to be 1 over cosine of theta. So if we actually multiply this with T0 cosine of theta 0, we obtain T is T0, and cosine of theta 0, we can eliminate the term from the denominator and the denominator, so we obtain something like this. Sine of theta 0 divided by L RCM. And also we found actually a T0 in part A. We found T0 in part A, which it was something like this. And I can paste it here. I want to paste it here. Oh. And then I want to, yes, it is correct. And then I want to substitute this T0 in this, so I can say that T is just M RCM omega to power 2 divided by 2 sine of theta 0 LRCM minus R squared sine of theta 0 divided by LRCM. And we can actually eliminate this RCM from both sides and say that T is just this. T is just something like this. we found t function of r as a function of r. So this is part D of the problem. Let's go to the next part. Next part says that find the maximum actual distance of rope from the line AB. It means it wants us to find R max. We had actually R as a function of theta. Let me to find here we obtained actually R as a function of theta. So as you can see here, because the cosine of theta is always positive, the cosine of theta, sorry, it is theta 0. The cosine of theta is always positive. Cosine of theta is positive when you actually move along the rope. So and it is a minus term. So if we want R to be a maximum, we will have to actually do theta equals pi over 2 to actually equals let me call it theta prime. When we do this, actually we understand that cosine of theta prime is going to be 0, so R max square is going to be LRCM cotangent of theta 0 times 1 over cosine of theta 0, which it is actually LRCM divided by sine of theta 0, which R max is going to be just radical this term LRCM over sine theta 0. And this is the last part. And also this is the last part of the question. We actually solved this problem, and we saw that the only actually note and the positive note of this question was actually part E. And sorry, it was part B, that we should actually take and small element of rope and actually write Newton's law for that small element and do some calculus and also geometrics to find actually the equations in both two directions, and do some calculus to find the length of this differential element, to find the mass of this differential element, so that we can find two actually differential equations. We can obtain actually two differential equations. So we solve them in both directions, in both x direction and y direction, and also there were actually notes how to actually solve some differential equations like this, with this actually changing in parameters. We actually changed the we actually changed the parameters here, and we used this note that f double prime is going to be something like df prime over df times f prime, and then we actually found the answer by integration, and we found the distance as a function of theta, the distance of each point of rope from line AB with the function of theta, and we also found T, the tension, as a function of the distance of each point from the line AB, and we at last we found actually the maximum distance which the rope has from the line AB. If you liked actually this question, if you like this problem, it was Iran's physics Olympiad problem level 3 again. If you like this problem and if you actually want us to record another videos solving differential equations and write actually differential elements and sorry take differential elements and write differential equations for them by using Newton's law and something like that, if you want us to actually record actually electromagnetism or thermodynamics problems, please comment below for us, and we will actually record some videos for you. And just that, thanks for your support and thanks for your watching, and bye.